Our next result is theorem 3.2.3. Has two parts, two properties of these so-called open sets. The union, the first property is that the union of an arbitrary collection of open sets is open. The second property is that the intersection, the finite intersection, or the intersection of, in case you want to see it that way, intersection of a finite collection of open sets is open. So a few comments about these two properties. So with these two properties and the property, and with these two properties, this collection of open sets, together with the empty set and the real line, so the real numbers. So this the largest set contained within R, which is R itself. So with these two properties and adding these two other sets, the empty set and the whole space R, we have that this collection together is a topology. This is something that you'll probably see in a point set topology course if you continue studying down that line. I mean, if you are interested in this kind of more abstract things, what this shows is that the set of, if we define open sets in this way, the collection of all open sets together with the whole space and the empty set form what is known as a topology. Well, now, so this is just in case. I mean, you read something that it's mentioned of topology. Now, this is what they're referring to. And yeah, and this is something you may also encounter. And usually things, you start from the other way around. You concern with topologies and then prove that certain collections of sets define a topology, and that the sets defining a topology are called open sets. Here we started from the definition of an open set, and then we're showing that this collection satisfies two of the main properties of a topology. The collection of these sets satisfy two of the properties of being a topology. Now, here I want you to pay attention to this word here. This is an arbitrary collection. People tend to think that when they think of an arbitrary collection is that it may be infinite. Not only can it be infinite, but it can be an uncountable union. The union here of open sets does not need to be countable. It can have a very large cardinality. I mean, it doesn't matter how many, even if you count them around, enumerate them. That's what countable means. A countable union or not. If you take the union of all these open sets, you will end up with an open set. There is a restriction, however, when it comes to intersections. So for the intersection of open sets, so in order for us to guarantee to ensure that this intersection is going to be an open set, we are limited to taking intersection of finitely many open sets. Later on, just very quickly, we're going to define closed sets. And closed sets are just complements of open sets. So that's what closed sets are. So we'll have corresponding properties. So the union of so the finite union of closed sets is going to be closed, and the arbitrary intersection of closed sets is going to be a closed set. Okay, but now so let's see the proof of this fact of these two properties. Let's say so for property I. What is an open set? Remember, an open set is a set that satisfies this property. For all A in the set, there exists some positive epsilon such that this whole epsilon neighborhood of the point is contained within the open set, the given set. So that, if that is true, then you can call that set an open set. So we must start by taking an arbitrary number. An arbitrary element. In this case, a number, a real number. So let A be in the arbitrary union. So lambda in lambda is an arbitrary union of open set word. So lambda is a collection of open sets. Okay. Given the definition of open set, we have to separate into cases here. So if, for instance, all of the A lambdas are the empty set, and that can happen. Why? Because here the property that defines an open set is that for all A in the open set, in the candidate for an open set, there exists an epsilon. But of course, if there's no A to check, then the statement is immediately true. So whenever we have a property like for all elements in the set, something happens. When you have the empty set, immediately satisfies that property. Because if not, then there would be an element in the set that doesn't satisfy the property, but there's no element in the set. So the empty set is clearly an open set. So that's what I mentioned at the beginning. That's why it's convenient to specify. I mean, depending on how you phrase things, you may need to add the set R and the empty set by hand. Here also, of course, R satisfies this property as well, because if you take any number A in R, actually any epsilon neighborhood of that number is going to be in R. Is going to be contained in R. So the empty set and R are automatically open sets. So there's nothing to verify. I mean, as he said, they're automatically set to satisfy this property. This property here, the for all element in there, there's an epsilon such that this holds. So the key point is showing that this is the set of an open set defined in this way. The collection of the sets is a topology. The main thing is to verify property 1 and 2, and from theorem 3.2.3. So, but let's go back to the proof. Here we let A be an element in the arbitrary union. If this union is empty, there's nothing to show. So if the union is empty, there is nothing to show. That's why I said let A be in the union. Right? Because if the union is empty, there is nothing to show. So this refers to the case, so let me put this in parentheses, it's better. Okay, so now that we have an element in a union, we know that at least one of these AA lambdas is not empty. So this is, I mean, the proof here just boils down to how comfortable we are dealing with set theoretic statements. So because now everything boils down to saying, so A belongs to the union implies that there exists some lambda 0 such that A belongs to A sub lambda 0. So A must belong to at least one of these elements in order to belong to the union. In order for A to belong to the union, it must belong to at least one of these sets. And once you know that, you can say, well, but then since but this is an open set, so this implies that there exists some epsilon greater than 0 such that the epsilon neighborhood of A is contained within A lambda naught. But A lambda naught being only one element, one member of the family, so one of the sets in the family, then it's clearly contained in the union of all the elements. I mean, of all the members in the family, so all the A sub lambdas. So you started with an element here in the union, and then you shown that there is an epsilon such that this epsilon neighborhood, positive epsilon such that this epsilon neighborhood of A belongs to the union. I mean, it's contained in the union, and that is exactly what it's exactly what it means for this set to be an empty set. So this is the definition of an empty set. Tells you that if you pick any element in here. So we picked an arbitrary A in the union, and we found a neighborhood that's contained an epsilon neighborhood of A that is contained in the union of these open sets. So that shows that the union of A lambda is an open set, provided that each one of these A lambdas is an open set. So for the second property, let's see that if the intersection, now we have an intersection of open sets, and if the intersection there is nothing to prove. So here, let me just phrase this again. So here, let me be more specific. So let's start with a different. So let A. Remember, just to stress the fact that we are only dealing with finitely many open sets. Let A1 up to AN be open sets. If the intersection is empty, there is nothing to show there is nothing to show. If instead there is an element, if A belongs to the intersection, however, there's an element in intersection, meaning that it belongs to each one of these open sets. Implies that A, again, this is again, now we go, we have to deal with this set theoretic statement. If, I mean, what it means for A to belong to an intersection. So, belonging to an intersection means that A belongs to AI for all I from 1 up to n. Right? So it belongs to each one of them. Belonging to the intersection means that A belongs to each one of the sets here, the open sets, AI. But since it belongs to each one of these open sets, I mean, these sets are open, that there are epsilon I equals 1 up to n, such that the neighborhood with epsilon I mean this epsilon I, these epsilon i's are greater than 0. Epsilon I neighborhood of the epsilon I neighborhood of A is contained within AI, because A belongs to the open set AI. That means that there is an epsilon I, of course depends on the open set, such that this epsilon I neighborhood is completely contained within AI. This holds for every single AI. But so how do we find an epsilon that works for each one of them? I mean, maybe some, if you think about this way, so let's consider this open set and this open set. So for instance, if you take this element here in this intersection, this may be some epsilon 1, while you may have another epsilon 2 here. So this one works for this set, while this epsilon 2 works for the other set. This epsilon 1 doesn't work because it intersects the exterior, so the complement of this set. However, this one here works just fine. It's contained within this set, and I mean with this radius, with this smaller radius, this epsilon neighborhood is containing both open sets at the same time. And that will be, I mean, that's what was going to help us. I mean, just it's going to allow us to say that this intersection is actually an open set, because we're allowed to take the smallest of all these numbers. And then you see why we need to take, I mean, we're only allowed to take finite intersections, because it could be that each one of these epsilons gets smaller and smaller. So suppose you have a countable intersection. And so, yeah, for each one of these open sets indexed by n, say, I mean, we can think of it as, think of a countable intersection, and each one of the elements have an n as subscript. So if you have that each epsilon n is, say, 1 over n, then you cannot take the minimum. You can take only the infimum if you want that to work for all the sets, but then the infimum is 0, so you don't actually have a positive epsilon in the end that will guarantee that that epsilon neighborhood is contained within that set, the intersection. So that's a problem. So you need to end up with an epsilon that will work for each one of these sets. So you need to take sort of the smallest one. And if you take if you consider an infinite collection, then that minimum may not exist. The infimum, of course, is you tend to think that's a kind of a good substitute, but in this case will not do, because the epsilon in the definition of an open set needs to be positive, and as we just saw, that infimum may be equal to 0. So, but okay, so going back to the proof, here we're in the situation where we're not taking an arbitrary intersection, but and not even like not only are we not taking an arbitrary intersection, we're only considering finite intersections. So we have this property here, right? That for each I, there's an epsilon I, a positive epsilon I, such that the epsilon I neighborhood of A is contained within AI. Okay, but now, so since well, we're going to find, so that epsilon is going to be the minimum of the epsilon i's, I equals 1 to n, right? And we know that this is positive because the set over which we're taking the minimum is finite. Over a finite set. In fact, in fact, I mean, this here exists because we are dealing with a finite set. Right? So even the fact that we're talking about the minimum, I mean, we're allowed to take the minimum. That minimum exists. Is already a consequence of the fact that we're dealing with a finite set. But also, I mean, that also implies that this minimum is going to be positive. And this is the difference again with the infinite case, because I mean, when you take, I mean, the minimum may not exist, but even if you take the infimum, that infimum may not be positive. Okay, so so with that epsilon bar, we'll see that so here what we made, we defined an epsilon bar. We have that for all I equals 1 up to n, since we chose the smallest one, the epsilon bar neighborhood of A is contained in the epsilon I neighborhood of A, because the epsilon bar is less than or equal to each one of these epsilon i's. Okay, so it's never bigger than any of these epsilon i's. So this epsilon bar neighborhood is going to be contained in each one of these other neighborhoods. And this is contained in AI. But this is true for every AI. And this epsilon bar doesn't depend on AI. So if it belongs to each one of them, so this is the for all here plays a role. Remember, if every element here belongs to this to each one of the AIs, it means that every element here belongs to the intersection. So this is contained. Also, this implies that this epsilon bar neighborhood is contained within the intersection of the AIs from equals 1 to n. Thus showing that this is an open set. So the final intersection of open sets is an open set. All right, so that's that's it. That's everything we can basically say about open sets. Now for closed sets, as I said, there's something that it's not the way it's defined here in the book, but it's a way that it actually makes more sense, especially once you've studied topology. You can basically define closed sets as complements of open sets. So closed sets are the same thing as complements of open sets. In fact, this is here derived later on as a consequence. As something equivalent to being a closed set using a different definition. But yeah, this definition I'm telling you now it's more natural, and you can use whichever when you're taking an exam with me. For me, the thinking of closed sets as being complements of open sets is the natural thing to do. But of course, the other properties, the definition that they use here are like useful properties when you want to show that a set is closed. One comment about the closed sets is that closed sets are, the negation of something being an open set. So if you say something is not an open set, does not mean that it's a closed set. And also, in the same way, if you say something is not a closed set, that doesn't mean that it's an open set. It's not to confuse complements with something not satisfying a property. Okay? So it's very important to make that mistake. Okay, so that's something that I see very often. But it's, of course, very incorrect. So we'll start with the closed sets then next time. Okay. Have a good weekend.